Hello everyone. So today we are starting project 3 of the Planet course. I'm quite excited for this one because this has easily the most interesting techniques to me, and I think you guys will enjoy this quite a bit too because this will definitely elevate your Planet renders quite substantially. And a lot of this part of the course is going to be focused around the creation of these cloud VDBs that you see here, which are critical for creating these larger cloud structures. If you recall from last time, we were kind of limited to these flatter cloud layers. Not anymore, my friends. We have access to these really cool cumulonimbus clouds now that we can definitely use to create some sweet renders. And here's one of them up close. You can see I actually used this one in this render. You can match the features up here. These are super detailed. I love them so much. All right, so let's discuss what we will be covering today. So we're going to be focusing on creating a basic simulation, and that means just creating all the larger details that you see here, but we aren't quite focusing on the finer details like the disturbance and such just yet. So there are 3 steps to this. So we're going to start by creating the emitter image, which is something that you can see over here. It's essentially just a mask of where our clouds will spawn. And this will be fairly simple. We're just going to be using the cloud tiles that we used in the second project to create our maps over here. Then we'll load it into Houdini and use it to set up a basic simulation. And you guys have probably just seen Houdini and been like, oh no, it's Houdini. What am I going to do? And I want to dispel some of the myths that surround Houdini. So number 1, Houdini is expensive. Houdini Apprentice is free and has everything that you need to follow this tutorial. You can pick it up from sideeffects.com. Number 2 is that I'm not smart enough for Houdini, and that is just false. You are smart enough for Houdini if you know Blender or some other 3D software. It's not any more or less difficult once you get familiar with it. And lastly, if you're brand new to the software, I'd recommend watching some content for beginners. This will be more beginner focused, but some background knowledge about the software definitely helps. So I'm not going through like keybinds and such just yet, but I will be covering this at a bit of a lower level so that you can hopefully follow along if you have a little bit of experience. But having some background knowledge, as mentioned before, would still be helpful. So without further ado, let's start by creating our emitter image. In GIMP, I've loaded in a tile that I got from the Landsat dataset, which you can find on Earth Explorer. Please refer to episode 2 of the course if you don't know how to do this. I cover how to get these tiles in fairly good detail. So first thing I'm going to do is I'm going to go to the levels here. I'm just going to clamp these values so that the gray value is not there. So, all right, so that's good. I'm going to turn this gamma value up a little or down a little bit, however you want to interpret that. That way I can just see which values are truly black and which ones are only look black. So now I'm going to take a subtract brush here, and I'm just going to mask out the edges so that we don't get any seams. And then we want to mark out the area of clouds that we want to keep, which is honestly going to be a fairly small area because we want to keep the amount of clouds for our simulation fairly low, just as a memory saving and time saving sort of thing, because the more clouds that you have, the more area that simulation has to run over, and you'll more likely run out of RAM, and it'll take a lot longer. So now we know roughly where we need to mask out these clouds and where we want to keep them. All right, so now that that's done, we can export our image. So I'm just going to export it to a file that I've already created. And lovely. So let's go into Houdini. Alrighty, so in Houdini, we need to start by adding a geometry node. And this will put us into the what's called the SOP context, which is the surface operators. So this allows us to mess around with our geometry in the scene. It says surface, but I mean, you can also do volumes and such, and that's what we're going to be doing today. We're going to be doing a lot of volumes stuff. So we need to start by creating the emitter object for our simulation. So what is an emitter object? It's essentially how the simulation sources its various attributes like density, temperature. It could also source velocity or pressure, or anything of that nature. So it takes in a set of volumes and then it uses those to inform the simulation. And we'll get to the simulation itself in a little bit, but let's start out by creating that emitter. So we need to add in a volume node. And then I'm also going to add in a null node. And this is going to be our simulation parameters. So I'm just going to call this simulation params. And what we want to do with this volume is we want it to be more or less a flat sheet that we can apply our texture to. So I'm going to change this uniform sampling to by size. I'm going to set the division size to 1 just to start out. And then in this null node, you can go up to this gear icon and then click Edit Parameter Interface. And you'll see now that we have this dialog. So what we can do is we can add in a float vector 3. And this is just going to be called emitter dimensions. And then, so that's the name. Then we can copy this to the label and replace the underscore with a space. And then I'm also going to add in another parameter here, which is just going to be a regular float. And then I'm going to call this voxel size. Brilliant. So now I'm clicking apply and then accept to close the dialog. And then what I'm going to do here is I'm going to change this voxel size up to 1. Then I'm going to right click on this. I'm going to click copy parameter. I'm going to paste it into this division size. I'm going to do that by right clicking and then clicking paste relative references. And now you see this turns green and there's an expression in here. And this is now linked to this voxel size. So if I change this up, you can see this is now changed too. It's somewhat like drivers in Blender, but honestly, this is a much more sophisticated system, and it's quite cool. And then we're going to do the same thing with this right here. We're going to copy the parameters here, and then right click on the this little box here, this light gray box, and paste relative references, and just verify that this all works. So let's change this to 1500 on the X and Z axis, and then like 2 on the Y axis. Alrighty, brilliant. And we can change the like initial value to see if it works. And it does. And then we also need to add in a name here. So I'm just going to call this one density. So why are we using 1500 by 1500? And why is this Y value different? So the Landsat tiles are 5,000 pixels by 5,000 pixels across. And each pixel has a resolution of 30 meters, right? So each pixel is 30 meters. Yeah, represents 30 meters. So that gives us a total area of those Landsat tiles of 150 kilometers by 150 kilometers. You can directly like add in or simulate at that resolution or that scale, but I just find it easier to simulate this in like 1 to 100 scale. So that's why we have 1500 by 1500 meters here. That's just, of course, 1/100th of 150 kilometers. And then the Y value in Houdini, Y is up. It's not like Blender where X and Y are the 2 horizontal dimensions or axes. In this case, X and Z are the horizontal axes and Y is up. You can see that because there's red and then there's blue over here. All right, so this is all well and lovely, but we don't see anything. So what do we need to do? So I'm going to right click and add in a volume VOP. connect this up to the first input. And this is where we're going to load in our texture. So I'm going to call this load texture. Fantastic. So I'm going to go up to this null parameter interface. And I'm going to add in a file image. And I'm going to call this emitter image. Fantastic. I'm going to click apply and then accept. And I'm going to find the image that we just created. Sweet. So now we have the path to that image loaded up here. So I'm going to copy this parameter. I'm going to go into this load texture node. I'm going to add in a texture node. And I'm going to paste this into the texture map field over here. And then we can connect the UV up to the position and then the color up to the density. Although I'm going to, because the color is a vector represented by this green color, the density is just a float. We want to just grab a single channel. So what I'm going to do is I'm going to add in a vector to float. Connect these up here. I'm just going to choose the FL1, which is the first channel, which is the red channel of the image. And you'll notice nothing's happening. So why is nothing happening? If you were paying attention earlier, you'll notice that I said Y is up in Houdini. And if you recognize that, you might also recognize that UVs are represented in the XY space, right? Usually your texture coordinates are X and Y, or red and green, because textures are 2D and Z is generally related to 3D. So to get this, to transform this X and Z coordinate space into X and Y, what we need to do is we need to add in a vector to float, and then a float to vector. Then we're connecting up the P into the vector, and then we're going to grab the FL1, connect it to FL1 here. So we're just reusing the red or X-axis, but we're going to say, hey, we want the Z-axis to now be the new Y-axis. So we're connecting up the FL3 to the FL2 over here. And then we're going to connect this up to the UV. And still nothing's happening. But that is okay too, because we can fix this as well. So right now we're just taking the coordinates of the position in 3D space and converting it to a UV coordinates. But we have a very large coordinate space, right? Like our plane is like 1500 by 1500 meters across, right? So this isn't necessarily like our texture is tiling a bunch, right? Because UVs are also mapped generally between 0 and 1, right? So if we do something like add a divide constant node, oops, set this to like 150, I guess. You can see now that we have that, our texture is tiled across the plane, which is brilliant. But we want to find a bit more procedural way to do this, that we don't have to manually change the value every time we like change the size of our emitter volume. We want it to update accordingly. So I'm going to delete this. And then what I'm going to do here is I'm going to add in a fit range unclamped node down here. And I'm going to add in two parameters. I'm going to call this one min bounds. I'm going to change the type to vector. I'm going to connect this to the source min. And then I'm going to duplicate this and call this one max bounds and connect it to the source max. So what we're going to do here is we're going to use these to load in the bounds of our source volume. And then we're going to map those, or map this position from those min bounds and those max bounds, right, to 0, to that range from 0 to 1. Right, so now we'll have like one texture tile that gets mapped over the entire emitter, and that is what we want. So how do we do this? So what we can do is we can use an expression in these boxes, and the expression is called bbox. So bbox, and when I add a parenthesis, you can see it gives us some information about it, right? So we need two inputs, right? We need the surface node, so the node that we want to extract the bounds information from, and then the type of bounds that we want to get. So we can either get the x-min, y-min, z-min, right? So these are the minimum boundary or bounding box coordinates for the x, y, and z axes respectively, or the x max, y max, z max, which are the maximum values of the whatever the bounding box coordinates. So what do we do here? What was the surface node? This type is a little bit easier to understand. We can just input one of these. How do we get a surface node in here? Basically, what we need to do is we can copy this node here, this volume, and then paste it in here, and it creates this path, right, to the node. So we can see we're going through the object context, and then GO1, and then now we're referencing volume 1. And we also, since this is a string, we need to place it in quotation marks. And then if we add in a comma, and then add in our the type, right, this float type, I'm going to call this dxmin. We can see this is now loading in the minimum coordinate for the boundary box of this volume 1 node. But we can make this actually a little bit simpler. We can replace this by just this number 0. So what the heck was that? What did we just do there? 0 is a shorthand for saying the first input to this node. So, and then 1 would be the next input. We can see 1 is not going well, but if we connect this up here, you can see we get the same result. So that's a very good way to just very quickly load in a on reference to the node. So I'm going to copy this to the other channels here, and then we want the y-min and z-min as well. This is going to be z-min. And then also can copying these to the max bounds. So x max, sweet, y max, and z max. Brilliant. Yeah, so now we have just one texture tile spanning the whole volume, which is excellent. This is exactly what we want. Alrighty, so now we have a very, very basic emitter. So let's create a simulation to feed that emitter into. So I'm going to create a DOP network. So DOPs are dynamic operators. So these are what you use for most of the simulations that you see. So what I'm going to do is I'm going to connect up the load texture to the first input. And then I'm going to enter this by double clicking. And then I'm going to create a smoke simulation or smoke solver sparse. Make sure you grab the sparse one. And then I'm going to create a smoke object, also the sparse variant, and connect that up. And then I am going to go up to the simulation parameters. I'm going to copy the voxel size parameter. I'm going to feed this into the voxel size parameter of the smoke object. And then lastly, I'm going to add in a volume source. I'm going to connect this up to the sourcing input of the smoke solver. So this volume source is where we're going to load in our fields from the SOP network, right? The ones that we just created. So in this input parameter, we're going to set it to first context geometry. So what this does is it reads from this first input. Inputs are also sometimes called context geometry. Don't ask me why. in the same way that we loaded in the first input for this B box thing. Brilliant. So now we need to add in an operation here, right? By just clicking this plus, and we're going to say the source volume is density, and the target field, which is the field that we want this to map to on our smoke solver, is density as well. And now, if the gods will it, we will have something loaded in here. Sweet. Although that's fairly pathetic. But we can see a couple things happening. So for one, the domain is expanding a bit, which is nice to see. And we can see stuff is being fed through the, or fed into this simulation. But this obviously does not contain the whole large field of what we wanted, right? So this is somewhat disappointing. So how do we get this to actually work? So one thing that you'll notice here is that when we zoom in, our simulation starts from 0, 0, and it kind of expands outward. That's what sparse solvers do. Sparse solvers expand the domain as needed. And right now, this is kind of getting choked up at this little point because there's just not enough volumetric stuff happening around here to justify it expanding into more of these like filled domains. So how do we get this to work? So for one, you can see we're starting from this little volumetric cube, and we don't necessarily want to do that. All right, editing Sam here. Just wanted to make a little bit of a clarification. So the reason why we don't want that tiny little cube in the center is because it's just not big enough to contain the entire emitter that we've created. So you get issues occasionally where you aren't like picking up on certain areas of the volumetrics. So what we're doing over the next few minutes is we're going to create this sort of initial domain that's matching the dimensions of the emitter so that when we start the simulation, all of our clouds will be able to be spawned just from the get-go and we won't have to fuss with it. So that's all. Back to the video. And to do this, we're going to right click and click allow editing of contents. And we're going to change the dimensions of this initial little voxel cube thing here inside of this smoke object. So if you enter this, you'll see we have a bunch of these little things. These are each loading in different fields for the simulation. So what we want from here is this vector field. And we can see that we have a size parameter and a center parameter. And this is just representing our simulation little cube here, right? So we need to use the bounding box information that we used before for our load texture thing, right? So this B box, we need to use that in here to make this properly sized, right? So what we're going to do is we're going to use the B box. And then I'm going to add in a quotation mark. And then I'm going to add in 2 periods and a /. And this says, hey, look for these nodes 1 level up, right? So these are relative paths. And you can see we get a list of nodes right here. So right now, this could reference any of these other nodes that we see in here. I'm going to add in another. And you'll see that now we're looking for nodes that we have in our in the parent DOP network, which is 1 level up, which is this .NET 1. And then we're going to add in another one here. And now you can see we have our load texture volume VOP in here. Same with our simulation params. So now we can add in one of these. For now, I'm just going to add the load texture and then close the quotation marks. And then since this is the size in the X direction, we're going to just use the dx size parameter here. And brilliant, we can see this is now stretched all the way to the ends. But I want to add in another node here, just another null node. I'm just going to call this emitter final. And this is just going to stick with this .NET nodes that's a little bit easier to reference. And I'm just going to change the reference, the node reference here, to the emitter final. Sweet. And make sure you only have one slash at the end of that. All right, so now let's copy this to the other channels. So we're gonna use the dy size for the y size, right? So that shrunk it. Very nice. And then the dz size. And we can see that this now encompasses the entire thing. Brilliant. And then the next thing that we need to do is we need to match up the center, the center here with the center of our volume up here. Right now the center is at 0, 0, 0, but if we want to say move our volume, say 250 in the y axis, this is not going to be represented by our current emitter configuration. So we need to add something in the center parameter here. And to this, we're going to delete the current expression, and we're going to use the centroid function, right? And this just gets us the centroid, the center in between the two boundary like edges for our object. And we're going to do the same thing that we did here. So just copying the path to the emitter final. Make sure you grab both the things. And then we're going to use the dx type. And then I'm going to copy this and paste it into here. Now setting it to dy. Brilliant. And we can see that that's represented, or that's moved us up like our emitter is currently. And then dz as well. And I'm going to stop with this silly business. I'm just going to put this back to normal. But now we have a properly sort of calibrated emitter. And if we go in here and then click play, have to free up the cache, we can see we now have our thingy working. And it's not doing much of anything, but we're at least loading in the texture, which is fantastic. So now it's just kind of cleaning this up. I want to, you'll notice when we have this, our clouds are going to be moving up, right? Like they're very buoyant, and we don't really want any of this stuff down here. So I'm going to treat y as closed below. And then just to be perfectly like flexible and such, I'm going to use the same b box thing and just using the dy min, right? So the minimum value of the y bounding box. So b box, same deal over here, emitter final, and then dy min. And kind of hard to tell if this really works because you can't really validate it, but this should theoretically do its thing. I guess I'm just going to test this by moving this up a little bit and see if it still works. And you'll notice it's not updating. I was wondering why that was happening for a second. That's because the frames are cached, and it will be orange if the cache is out of date. So I'm just going to move this back. All right, brilliant. This seems to work. Yeah, so blue cache is like when it's up to date, and then an orange cache is when it's out of date and you need to update it. All right, but enough of that silly business. Let's make this actually move, right? So what we need to add in for that is we need to add in a temperature field, because right now it's got zero information about where the temperature or where the volume should be moving. It's just got the density information, and that is not enough on its own. So we need to add in a temperature field to tell it that the simulation should be a little bit buoyant. So to do that, I'm going to add in a merge node. And what we're going to do is we're just going to copy the density field here and then rename it. So we're going to add in a name and connect this up. And this is, we're just going to call this rename temperature. So we see we have we have two parameters here. One is called group and one is called name. So name is just going to be temperature, as you might expect. But we need to tell it which volume we want to rename. So how you load in a volume here is you're just going to say, or you can actually just click down or click this arrow down here and then click the density volume right here. So we're renaming the density volume to temperature. And then we're going to connect this up to the merge node as well. And you can see if we click on that info thing here, we have, oops, that's a bit outdated. We have density and temperature, which is awesome. So let's feed the temperature into the simulation as well. So the field to match, we're going to add in the temperature here, just all lowercase. And then we're going to add in another operation too, which is going to be temperature. And for both the source volume and the target field. And then I'm going to just increase the buoyancy scale a ton because we can. And theoretically, we should see our thing start to rise up. Awesome. So now we have a basic simulation going. And from here, it's about refining the shape a little bit. Alrighty, so I see a couple things here that I'm not too much of a fan of. The first one is that pretty much the buoyancy everywhere looks pretty much equal. Right, so even these really small little bits are just as buoyant as these supposedly really dense bits. So we got to change that. So I'm going to add in another node here after the temperature, after the rename temperature thing. So I'm going to add another volume up. And I'm going to connect that up to the first input, like always. I'm just going to call this post-process temperature. So we're going to add some more parameters up here. And I'm going to add these inside of a folder. I'm going to call this folder temperature properties. I'm going to set this type to simple. And then I am going to add in a float here. And I'm just going to call this one temperature coefficient. Dude, my typing is something else today. Sweet. And then I'm going to add in another one here. I'm going to call this temperature gamma. I'm going to change the defaults for both of these to 1. So now we have a couple parameters that we can use to control the density or the temperature. So how we're going to control this temperature is I'm going to first delete both of these nodes in here. And then I'm going to use the bind node here. And we're going to bind this to the temperature. And then we can copy this. I'm going to paste it. I'm going to check this parameter right here. Use this node to set parameter attributes. And then I'm going to, under export, I'm going to say when input is connected. And now I'm going to connect the temperature here to the temperature there. And now we can add in a multiply node. And I'm going to add in a parameter node. And I'm going to call this one temperature coefficient. And connect this up to the second bit. And then I'm going to copy this parameter here and then paste it in this temperature coefficient slot right here. And now when we change the temperature coefficient, we are doing something. We're changing the density. We're changing the amount of temperature that we have, right? So now this temperature gamma is going to control kind of the contrast of that temperature. So we're going to add in a power node. And then we're going to duplicate this temperature coefficient, then rename this to temperature gamma, and then plug this into the second exponent input. And then do the same thing where we copy the parameter and then paste relative references. So now if we play with these, I'm going to turn the gamma up quite a bit, and then the coefficient up quite a bit too. We will hopefully see a little bit better results here. I'm just going to let it cook for a second. Alrighty, so this is much better, right? Where you see we have these much more convective portions, and then the little guys down here, they're still a little bit mushroomy, but that can be fixed. We got the main stuff working, which is brilliant. Just going to give it a couple more frames. Alright, so I let it go for a couple more frames, and you can see kind of what's happening here. These are definitely looking somewhat cloudy, but I don't like how straight up they are. Clouds usually have some sort of shearing happening to them. All right, editing Sam here with a point of clarification. So wind shear is essentially the difference in wind velocity between the bottom of the clouds and the top of the clouds. So this is a really good example of that. You can see that at the bottom, the clouds aren't moving as fast. This is a very sped up time lapse, but at the top, they're moving a lot faster and in a completely different direction actually, which is really cool. But something to note here is that they're kind of all being emitted from a similar place. By the way, I will link this video in the description, or at least I'll try to remember to. So there's just a bunch of clouds that are being spawned over at whatever, there might be a lake there or something. And the wind is pushing them all like backwards, right? So what does that look like in our simulation? So here's the simulation from a couple minutes in the future from your reference point. We're going to be making something, well, we are going to be making this. This is literally just from the end of the tutorial, right? So we're moving the emitter, and this is causing the new clouds to be spawned like somewhat in front of the old ones. And it's creating this really nice profile as opposed to just being straight up like little mushrooms. So this is much more desirable, and we will be making that in the next few minutes. Back to the video. So I'm going to add in a transform node, and what we're going to do here is we're going to add in some more parameters. I'm just going to put this in another folder called emitter animation. Also going to set it to simple. And we're just going to use another vector parameter here. And we're just going to call this emitter velocity vector. And then the same here. Just remove the underscores. And then we also want to add in a parameter, float parameter called emitter velocity or emitter speed. Brilliant. I'm just going to set the default here to 1. All right, so emitter speed should control how fast we're moving, and then the velocity vector should control which direction we're moving. So I'm going to set, yeah, so this is just going to get set to 1, 0, 0. And then we can copy the parameter here. I'm just going to paste this into the translate. You can see that moved it a little bit. And now I'm going to copy the emitter speed, and I'm going to paste this into the, so I'm going to enter each of these boxes. I'm going to put the asterisk there for times, and then paste relative reference here. And I can just copy this and paste it over. I just need to change the X suffix to Y for the Y axis, and then the X to Z for the Z axis. So now we have this translated over by like 1, 0, 0. Brilliant. And we can see if we increase the speed, this is going much further. But this isn't like an actual animation, like it's still stationary. So what we need to do is we need to add in the time component as another coefficient here. So, or not coefficient, whatever. We're going to add in this hashtag, or not, sorry, not hashtag, $, and then in caps, just type T, and then copy this to the other ones as well. And now you can see we are moving. This is quite slow, so I'm going to turn this up to like, yeah, 10 maybe. And I think that's pretty good. Maybe a little faster, 25, so that we can see it moving. Brilliant. Now in our cloud tile, we can see the clouds are kind of moving like this way, right? So I think we might want to do that. So let's see, which way do we want it to move? So we want to move negative in the negative z-axis and the positive x-axis. So negative z, positive x. So let's just say maybe -1 here. And I think that's pretty good. Maybe lower this down a little bit. So I'm going to simulate this and give it a test. All right, so this is what it looks like after a little bit of simulation. And first of all, I love the shapes here. I think we might need to tone down the buoyancy a little bit, but this is pretty cool. Secondly, something's happening here, and you guys can probably guess what's going on. So our emitter has very fine details on it that are being dragged with the simulation moves. And it wasn't super offensive in the previous iteration where it wasn't really moving, but this is quite obnoxious. So we need to break that up a little bit. So what we're going to do is we're going to use some noise to distort this texture a little bit, and we're going to animate that noise so that the texture is a little bit different for each frame. And this is going to just ensure that we don't have the weird streaks that we had before, because the texture is not going to be perfectly constant. So in this load texture, after the fit range, we're going to add in a noise texture. And just grab the anti-alias noise. And then we're going to use this as the position. And then I'm going to add in a vec to float, because we don't really need anything happening on the y-axis. We just need them on the x and z. So float to vector. So I'm just going to use the x and z axis, and then I'm going to connect the y axis to the time here. And then I'm going to connect this into the pose input. And then here I'm going to, after this, I'm going to add in a divide node. And then add in another parameter. And this is just going to control the scale of the noise. Make sure your parameter names don't have any spaces, so just replace them with underscores. So we're going to divide it by that. So I'm going to set our noise scale to be like 0.01. This is relative to the size of the texture. And then I'm going to set the signature to 3D input, 3D noise. And then I'm going to add in an add node, and we're going to use this to, we're going to add this to the UVs for the texture. You can see we've done some wonderful stuff here. But we need to multiply it by the noise scale a little bit so that it is properly strengthed. So we can see, yeah, so this is changing up the texture a little bit, dithering it a little bit, which is exactly what we want. I'm going to add in another parameter here called noise strength. And I'm going to connect this to the amplitude. And this is just going to be sort of a coefficient for the strength. And then, of course, let's add these to our primary null node. So I'm just going to put this into another folder. I'm just going to call this emitter emitter properties. Also set to simple. And then I'm going to add in a parameter here called noise breakup scale. I'm going to set this to, as mentioned before, 0.01. And then this range, I don't need the full like 0 to 10 range. I'm just going to say, hey, 0 to 0.25 maybe. And then noise breakup strength. I'm going to set this from 0 to 2 probably. I'm going to set the default to 1. And this should load in our parameters here. So I'm just going to copy these and paste them in here. Now, I'm not super huge fan of the organization, so I'm going to put the these two folders inside of the emitter properties, and this is going to sort of create a little hierarchy and such. And we can also add in a folder for the noise breakup. So also set to simple noise breakup. Brilliant. So that's a little bit better for me. And now when we simulate our simulation, we should see that it looks a little bit better. So we can see that this is clearly an improvement from before, but we can probably add in a little bit more noise breakup here just to make it a little bit less pronounced. But this is honestly quite good. We can clip we'll be clipping the bottom of these. Well, yeah, we'll be clipping the bottom of the VDB anyway when we finalize it. So this won't be too offensive. I do think it will be worth it to just increase that noise strength a little bit, or the noise scale probably. And that will probably do the trick. All right. So I'm going to leave it at here. The last thing that I want to do is show you guys how to take the output of the DOP node and bring it into the SOP context, right? Which is this geometry node. And we can use the DOP import fields. And we just connect our DOP node to our DOP network. And then we need to add in a field to import. We're going to add in the smoke object sparse. And the field that we want is just density. So if I just give it a couple simulation steps, we can see that this now works, which is brilliant. All right, so I'm going to leave it at here. In the next episode, we will be adding some forces to our simulation to give us a little bit of breakup on these little plumes so that they actually look a little bit more like clouds, and just really crafting and fine-tuning the simulation until we have something that looks stellar. But this is a really solid base, and I'm going to leave it here. The only thing I do want to do is I want to show you guys how to convert this from a volume to a VDB. What's the difference, you might ask? Who knows? No, I'm just kidding. VDBs are much more efficient at storing volumetric data, so it is useful to work in VDBs after you do your simulation, but simulations are run over your volumes. So we're going to convert VDB and then connect this to the first input and then convert to VDB, and voila. So I hope you tune in next time. The next episode will be out in a couple days when I finish recording it and editing it. And yeah, that is it for me. Join the Discord in the link in the description below. We would love to have you. We have a lot of resources dedicated to plants and stuff in there, including a dedicated thread for this course and a bunch of very talented people doing very talented people things. So yeah, that is it. I'll see you guys later. Bye.